Okay, so let's get on with our lecture. So today we're going to talk about kinematics, which is carrying on our theme of rigid body dynamics. So, what is kinematics? Kinematics is the relationship between motions. Okay, so it's the relationship between how different parts of our system move in relation to each other. And there's several methods of solution, but there's two that you all have come across. One is the velocity diagram. And the second is vector algebra. Okay, so students often ask a couple of questions. So quite often people ask, in the exam, will I be penalised if I use one method than the other? And the answer is no. In the exam, if you answer the question correctly, then that's fine. Okay, so the velocity diagram method, you'll have seen that last year in your first year course. Okay, and in some of the notes that I give out, you'll see a comparison with velocity diagram methods. But the method that we're going to use is the one we introduced over the last couple of lectures, and that's vector algebra. And so another good question to ask is, why on earth do we want to use vector algebra when it seems so complicated? And that's a good question. One of the reasons is that using this IJK notation, the vector algebra notation that we've started to develop, is a kind of first step towards a more sophisticated analysis called quaternions, and that's used extensively in the space industry. Okay, so when you have systems like space systems where everything has to be done in terms of a reference frame. Okay, so you have a local reference frame, you have a global reference frame or a planetary reference frame, and the thing is moving around in free space, then the dynamics become quite complicated. Okay, so this kind of analysis method is a method that can be used in those circumstances. Not that we're going to cover it in this course, but that's one of the reasons that we cover this approach in the course that we're doing now. Okay, so today we're going to talk about relative motion, and we're going to do a couple of examples to get ourselves familiar with the way these things work. Okay, so, and you'll have seen these types of expressions before. We've already mentioned them in the last lecture. If we've got points A and B, we can relate the velocity at A to the velocity at B plus the velocity of A with respect to B. And in the last lecture we said that can actually be written like this. It can be the velocity at B plus a rotation vector, omega AB, and then the cross product of that with a distance vector. Okay? So we got to that point in the last lecture, and so what we're going to do now in this lecture is we're going to go through a couple of examples to show you how we can make use of this in solving kinematic type problems. So the first example we're going to do is called a slider crank. Okay, so this is a classic mechanical engineering example. Slider cranks turn up in all sorts of machines and mechanisms. Probably the most well-known one is the internal combustion engine. Okay, so that's one area where they turn up. So let's draw a sketch of a slider crank mechanism. Okay, so the sketch looks something like this. Okay, so, and if you imagine that if it was inside an engine, then this would be the piston, Okay, so that would be the piston here. And what happens is that this part rotates around. Okay, so this part rotates, and by rotating, what happens is that the piston then slides backwards and forwards along the horizontal axis as I've drawn it here. Okay, so what we're going to do is we'll analyze this using the vector algebra method. Okay, and so if we label the points, we'll label this point O, the origin. Okay, and then we've got point A on the piston and point B here, where the slider and the crank are connected together. Okay, so to make this sort of have some meaning, we'll give some dimensions as well. So we'll have 350 millimeters along here. This will be 125 millimeters. And this angle in here will be 60 degrees. The rotation speed of the crank will be given to us as omega equals 1,500 revs per minute. So that's revolutions per minute, okay, rev per minute. And we're asked to find the velocity of the piston. So in these types of problems, of course, you know, in the practical situation, this thing would be moving very quickly forwards and backwards, okay, and the thing will be rotating. When you're asked to find the velocity of the piston, you're assuming that it's kind of freeze-framed in its current position, okay? So the reason that you've got, you know, an angle of 60 degrees there, it's saying, assuming it's freeze-framed at this particular point, okay, work out the velocity and sometimes also the accelerations and so on. Okay, but it doesn't normally say that in the question. It just says work out the velocity of point A or the piston or whatever the question is referring to, okay? But it's assuming the dimensions and the point in time where it's at right now. Okay? So straight away from these dimensions, you can work out that this angle in here is approximately 18 degrees from the sine rule. Okay, so that's straightforward. But what we need to do is, from this diagram, is we need to come up with a kind of a diagram which relates our vector algebra and the velocities at A and B together. Okay? So what we're going to do is we're going to redraw the diagram in terms of the velocity components. Okay, so we'll sketch it out like this. We have point A here, point B there, and the origin O here. And of course, the other thing that we'll always try and do is do a little sketch in the corner of the I, J, and K components. Okay, so we're going to have I is in the horizontal direction, J is the vertical direction, okay, and K is the rotation. Okay, and it's always positive this way. So we say K out of page. Okay, so our rotations, as you remember, we defined taken positive that way always for this two-dimensional system with a rotation around the K-axis. Now if we go back to our slider crank mechanism, what we'll notice is that the piston is constrained to slide up and down along this axis. Okay, so its velocity can only be in this direction, okay? And as we're rotating the crank this way, okay, the logic is that the velocity will be going, the piston will be going like this. Okay, if we make a guess like this and we get it wrong later on, we'll get a minus sign, so it doesn't matter in some respects. Okay, we can make an assumption, work through, and then if we get a minus sign, it means that this guess was wrong and it's actually in the other direction. Okay. Likewise, if we've got a velocity at b, the velocity at b is rotating around in a circle, isn't it? So we'll have a vb vector like the tangent to the circle of that crank. Okay, and then that will be, because we know this is 60 in here, that will be 30 degrees in there, won't it? And then we'll also have a VB relative to A vector going up here. Okay? And if you think about what's happening with this motion, if you think about, I know I'm freeze framing it, but if you think about what's going to happen in the next sort of second or so, as the crank rotates to the right, this thing is going to be moving up and around. Okay? And in fact, what we'll show in this analysis is that we can actually treat that as a circular motion around this point A. Okay? In which case, this VBA is also moving like a tangent on the circle of motion. Okay? So we can write down the relationship either way round. So let's write down B is VA plus V of B relative to A. And we can sort out our rotation speed. Our rotation speed is given in non-standard units, isn't it? So we need to change that to radians per second. So what we're given in the question is an omega. Okay, so let's label it omega 0 to B. Okay, so that means this is point 0, this is point B. So if we've got omega 0 to B, it means the rotation of omega relative to B. Okay, so that's why we've labeled this 0B here. And let's change this to rads per second. So we've got 1500 revolutions per minute. So we divide by 60 times by 2 pi. Okay. And what happens if we calculate that? What do we get? What's the answer? Who's got a calculator? Perfect, yeah. 157.1 rads per second. So, now what we're going to do is, whenever we have a situation like this, where we have a rotation of a crank around a point, okay, we're going to use this kind of notation, okay, we're going to use this to find the velocity. Okay, so here we've got VB is rotating around this circle, which is going to be drawn out around here. Okay, so this distance here is the radius. Okay, so that would be radius from O to B. Okay, this thing here is this rotation speed, omega OB. So if we cross product this with this rotation, we'll get VB. Okay. So the velocity B is equal to this cross product of this vector omega OB crossed with another vector ROB. So just to be clear, this thing up here, I haven't called this a vector, this is a scalar, right? Because it doesn't have a little line underneath it. Okay, so this is just a quantity that was given to us in the question. To get this vector algebra to work, we have to turn that into a vector. Okay? And to do that, what we have to notice is that if you look what's given to us, we're given a direction and a magnitude. Okay? And how does that relate to our rotation around the k-axis? Okay, well the direction is opposite, isn't it, to our positive convention. Okay? So it's going to be equal to minus the scalar omega OB times by the k vector. Okay? So what we're doing here is we're creating the omega underline vector, okay, by working out what the sign convention is, putting in the scalar quantity, and multiplying it by k, because what we defined for vector algebra is that rotations are a quantity and a magnitude times by the k vector, aren't they? Okay, so all of this thing here is basically that. Okay, and then we cross product with this thing, which is the distance vector r from O to B. Okay, and we can work that out using trig. Okay, so if we think again, we've got to think about it relative to our convention of I and j. Okay, so what's happening is if we start at point O and we want to put down the I component, we're going backwards. Okay, so we're going negative I in this direction, aren't we? Okay, so we're going to split this up into its components. We're going back that way, and then we're going up in a positive j direction. Okay, so what we get is minus R0b, that's the scalar length of the crank arm, cos 60 times I. Okay, so this is what bit of it is going in the I direction. So we're taking the scalar length of the hypotenuse times by the cosine to get this component here, and it's minus because it's going in the minus I direction. Okay, now the next bit's going in the positive j direction, so that's going to be plus the scalar length R0b sine 60 times j. Okay, so now it's a case of just working these things out. Okay, so we know that this scalar quantity for omega OB is 157.1. Okay, so we put that in. K crossed with, well, we can work these things out from the distances and the angles we've got in the question, and it comes out at minus 0.0625 I plus 0.10825 j. And if I multiply that out, okay, if I multiply that out, two things are going to happen. All right, first of all, I can multiply the numbers straight away. That's not a problem. Okay, but what I have to do is I have to remember that k crossed with I gives me something specific, doesn't it? So let's just write down what they are. So k crossed with I is equal to j. Okay, do you remember we did these in a previous lecture? And then k crossed with j is equal to minus I. Okay, so when I'm multiplying this out, the two things that are going to happen is that the numbers just multiply, okay, and then you have to take into account these multipliers as well. Okay, so if you do that, it should come out at 17.1 times I plus 9.82 times j. Okay, these are both positive values, aren't they? Because if you look, this is a negative times a negative, so it gives me a positive, but the k times the I is just equal to j. Okay, this is a negative times a positive, which should give me negative. Okay, but when I multiply the vector terms, I get minus I. Okay, so that becomes positive. Okay, so I end up with this as my answer for VB. Okay, so now we can do exactly the same thing as I mentioned before. If you look at the logic of what's happening in this picture, this motion is pushing this around this way. Okay, so this point, in the next couple of seconds, this point's going to go up that way, isn't it? And this point is A is going to move to the left, to the right. Okay, so we can treat that movement, okay, like a rotation. Okay, so we can assume that there's a rotation here, okay, going around there, okay, and then this is a length along here, and so we can assume that what's happening in that is exactly the same as a rotation, even though it's not going around a full circle. Okay, we can still use that rotation cross product with the length of the vector to give us this resulting vector up here. Okay. So that's what we're going to do. We're going to say that V, B with respect to A, is equal to omega AB. Okay, so this is a new rotation vector that I'm putting in, which is assuming the rotation around the point A for the length AB, crossed with the distance vector RAB. Okay, so that's the length in vector algebra. That's the I and j components going from A to B. Okay, so if I work that out, well, I don't know what this omega AB is, but I do know that this vector is a scalar quantity, omega AB times k. Okay, and then that's got to be crossed with this distance vector, and I've got some dimensions from the original question, so I know that the length of this thing is 0.35 meters, because it was 350 millimeters along that slider length, wasn't it? And I've got an angle cos 18 degrees. That's my I component. Then I have the same kind of similar thing for our j component. It's 0.35, but this time it's times the sine of the 18 degrees, and that's my j component. Okay, so what I'm going to do is I've got an unknown here, which is the omega AB, and for now I'm just going to leave that as an unknown. I'm going to solve that for that in a moment. Okay, so I'm going to multiply this out. Again, remembering that when I multiply k and I and k and j, I'll get some new quantities, won't I? So this, we do it in two steps. So first of all, let's just simplify this expression down to some numbers. So I think we get something like this. And then if I multiply that through again, I get the final amount is minus 0.01083 omega AB in the I direction plus 0.3328 omega AB in the j direction. So what I'm going to do now is I want to work out what omega AB is, and I'm going to take advantage of something you can do in vector algebra. Okay, what I'm going to notice from this diagram is that VA has to be in the I direction. Okay, so it can't have any j components, right? So if I look at this equation here, but just for the j components, this bit here is going to be 0, isn't it? Okay, so this one here is 0 for j. Okay, so it just means that this has to equal this for the j direction. Okay, so if I can notice that just by looking at my diagram. So what I'm going to do now is equate terms in the j direction to find omega AB. So if I do that in the j direction, I have, as I've just said, the VB is just equal to VBA, because VA has 0 in the j direction. And so, using my two expressions, I'll have 9.82 is equal to 0.3328 omega AB. Okay, and so omega AB is equal to 29.5 radians per second. So now, in the I direction, we've got 17.1 is equal to VA minus 0.1083 omega AB. So VA is equal to 20.3 meters per second. And so here I've left off the underline because this velocity now is not the vector, it's just the component in the I direction, isn't it? So it's effectively a scalar, and that's what this tells me here, that it's 20.3 meters per second. Okay, so that's the solution we were asked to find. So let's look at a second example. And again, these examples are all in the printed notes as well, in the printed lecture slides. Again, this is another one of those classical examples that you find in mechanical engineering texts about mechanisms and machines, 4-bar linkage. So we're going to use exactly the same approach. I'll draw the diagram of the problem, and then we'll use our vector algebra. But what we'll do is, wherever we can, we'll use this rotation cross product with a distance to give us our velocity components. Okay, and that will help us work out what the overall solution is. So in this case, the situation we've got is we've got a point here which we call the origin, and then we've got a vertical bar going up to a point A, and that distance is 100 millimeters. And then this bar slopes down to another point here, which is point B. And then we have a bar along here into point C. Okay, so this distance in here, it's not drawn to scale, that's supposed to be 50 millimeters. This overall distance here is 250 millimeters. And this thing is rotating around in a radius of 75 millimeters. And it has a angular velocity, omega CB, of 2 radians per second. And the question asks us to find angular velocities of the elements A, B, and OA. So we've got two ways to tackle this problem. We've got this point is fixed, point C, and this point's fixed, point O, and we've got these sort of rotations around those points, okay? So we can find the velocity at B, because that's equal to omega CB crossed with RCB, which is equal to 2 times K crossed with minus 0.075 I. Okay, yeah, I've forgotten to draw my diagram. I've forgotten the first rule of this vector algebra. Let's draw the I, J, and K diagram. I is that way, J is that way, and K out of the page. Okay, so hopefully you can see what I've done here. I've taken the omega CB and I've made a vector 2 radians per second times K. That forms my rotation vector. Cross product with, well, this distance from C to B is just in the I direction, and it's going backwards because we're going from C to B, so it's minus 0.075 meters, isn't it? Okay, so if I work out what that is, it gives me minus 0.15 J as my velocity. I can do the same for the point BA, the velocity at A. That's equal to omega 0A, which we don't know at the moment, times K crossed with 0.1 J. Okay, so this, I'm forming my vector here again, just because we're getting used to this going slightly faster, so instead of writing this down, I'm just going straight to this step. Okay, so I've got a scalar times K crossed with, this is now 100 millimeters going up in the J direction, so it's 0.1 times J. And if I work out what that is, I get minus 0.1 omega OA times I. Okay, so I'll leave omega OA there as an unknown, which we're going to find during the course of the solving the problem. Okay, and then I'm going to do the same thing that I did before. Okay, so if I look at the logic of what's happening here, this thing is rotating in this direction, which means that point B is going to come down, okay, and point A is going to move that way. Okay, so I'm interested in this element AB. This is the only thing we haven't worked out so far. So what I'm going to do is I'm going to treat, I'm going to assume that as this is moving down and this is moving across, that there's a rotation here, okay, around point B. Okay, so as this thing is going down and across like this, I'm assuming that I can work out the velocity of B relative to A, okay, as the rotation times that distance. Okay, so I'm going to assume that I can work out this quantity as a rotation omega AB crossed with the distance RAB. Okay, so if I work out what that is, well, I don't know what omega AB is, but I'll put that in as an unknown. But I do know what the distances are because I've got all the dimensions on the diagram. Okay, so I can, oops, sorry, I've done that the wrong way around. I was just looking at the wrong thing. This should be A relative to B. Apologies. And this is omega BA crossed with R BA. Sorry about that. Shows you how easy it is to make a slip. So this is V, A relative to B is equal to omega BA crossed with RBA. And so now here I've got scalar omega BA K crossed with, well, the dimensions I've got are minus 0.175 in the I direction and plus 0.05 in the j direction. I multiply that out, and I end up with minus 0.175 omega BA j minus 0.05 omega BA I. So now I've got all those sort of rotational type components. I can substitute into the overall equation that the VA is equal to VB plus VA relative to B. Okay, so let's try and do that. So what I would have on the left-hand side is minus 0.1 omega 0A times I. So that's what we worked out VA was. And that's equal to, well, we worked out the VB is minus 0.15 J. And then VA relative to B, this thing we've just worked out, has two terms. And that's minus 0.175 omega BA J minus 0.05 omega BA I. So all I'm going to do now is just try and match the coefficients, okay, because in the I direction and the j direction, just like equating horizontal and vertical components, I've got to have equal, it's got to be equal, okay, so let's try and do that. So if I do that, what I get is I coefficients gives me that minus 0.1 omega OA plus 0.05 omega BA equals 0. And then the J components, I have 0.15 plus 0.175 omega BA equals 0. So now hopefully it's clearer how it's going to work, because the J equation we can solve straight away now for, we can solve for omega BA, can't we? And so we end up with minus 0.86 radians per second. And then of course we can take that result, substitute it into the I equation and solve for omega OA. Okay? So omega OA would be equal to 0.05 times minus 0.86 divided by 0.1, which should come out at minus 0.43 rads per second. So we've found what's happening. Let's just sketch out what that looks like. Okay, so we've got this system like this. This is O, this is A, this is B, and this is C. And we started off with a rotation around C, which was 2 rads per second. And what we found is that we've got these other two rotations, okay, and they're both negative in our coordinate system, which means they rotate the other way. Okay, so this is a positive rotation. So this one that's rotating 0 to A, okay, so that's going this in this other direction, and its magnitude is 0.43 rads a second, okay? And likewise, this is also going in the negative direction, so this is a rotation like this, and this is 0.86 rads per second in magnitude. Okay, and it follows the logic, doesn't it? Because if this is rotating this way and this point's then coming down, following that circle, okay, it's pulling this down and to this direction, okay, and it's pulling this one in this direction. In the lecture notes, there's calculations for the acceleration. So there are calculations for the acceleration shown in the printed notes, but at the moment I want to do, there's a couple more lectures material to explain how the acceleration aspects work for rigid body dynamics before it's worth you tackling that particular type of question, okay? So when we come back after the Easter vacation, which I know you're all looking forward to, then we're going to do some more rigid body dynamics, and we'll do acceleration calculations then. Okay, other than that, I look forward to seeing you on Friday for the tutorial. Okay, thanks guys.